So last class we discussed discrete time Fourier transform, the DTFT. So DTFT being used to find the Fourier representation of discrete time non-periodic signals. Okay, and we discussed that okay, so DTFT in the frequency domain or the spectrum of DTFT is nothing but a periodic spectrum. It is a period of 2 pi. And it is continuous in nature. Okay, so also we discussed one example and to how to find out the DTFT of the signal. Okay, so today we'll discuss Fourier transform of continuous time non-periodic signal. Okay, so it is the continuous time non-periodic signal. Continuous time non-periodic signal, and its Fourier representation we call it the Fourier transform, and this is the most widely used Fourier domain representation, as because most of the natural signal they fall into this category. Okay, so when you say Fourier transform, basically we mean to the continuous time non-periodic signal, and you are representing with the help of the Fourier transform. Okay, so in the continuous time non-periodic nature of the time signal implies that the superposition of complex sinusoid used in the representation involves a continuum of frequency ranging from -infinity to infinity, right? So it is nothing but the Fourier transform. It says that it is the superposition of complex sinusoids which involves a continuum of frequencies ranging from -infinity to +infinity, right? So just like in the opposite to the discrete time Fourier transform, so here in that case also it was a superposition of complex sinusoids which is also continuum in frequency, but that the frequency ranges from -pi to +pi or 0 to 2 pi, as because it is periodic in nature. Okay, so discrete time case, it is the discrete time frequency is periodic nature, and that goes from 0 to 2 pi. Okay, but here in Fourier transform, so again it is nothing but any signal, any continuous time non-periodic signal can be represented as a superposition of complex sinusoid which involves a continuum of frequency ranging from -infinity to +infinity. Okay, then any continuous time signal x of t can be written as like this, 1/2 pi, so -infinity to infinity x of j omega e to the power j omega t d omega, right? Okay, so x of j omega is nothing but we call the Fourier coefficients, and this Fourier coefficient is multiplied to each of the frequency component present in the complex sinusoids, and you take the integration of all these things over -infinity to infinity. That gives me the representation of the continuous time signal. Okay, and then this Fourier transform x of j omega, or some group you may see this one is x of omega, and we can ask so that can be written as -infinity to infinity x of t to the power -j omega t dt. Okay, so This is nothing but we call the Fourier transform of x of t. Fourier transform of x of t. So again, this is again a bilateral transform. So x of t, from there using Fourier transform, we can go up to x of j. Okay, and then we can go back from x of j omega. Okay, so from frequency domain to x of t, which is called the inverse Fourier transform. Okay, so yeah, so this is called the Fourier transform of a continuous time non-periodic signal. Right now, let us look at what its characteristics, and with an example, we'll see how the Fourier transform look like. And if you see here, so x of j omega, the Fourier transform also it is continuous in nature. So omega is there, so it is continuous in nature, and it goes the frequency from minus infinity to infinity. Okay, but remember, in case of discrete time Fourier transform, so we have only the frequency ranging from 0 to 2 pi. Okay, because, and that is also periodic, so it will go on repeating after 2 pi interval, the spectrum. Right. Now let us an example how we find the Fourier transform of the non-periodic signal, continuous time non-periodic signal. So for example, my signal is x of t, is represented as e to the power minus at u of t, and then let us find out its Fourier transform. Okay, so as you know, so if I go on looking at this x of t, then this x of t is going to be bounded 1. Okay, so if a is mod of a is less than 0. Okay, so then that's why we can go on finding out. Let us see the bounding of this x of t. So if I look at minus infinity to infinity x of t, so dt, so it should be a finite number. Okay, so now if I let us see whether it is going to finite or it is having a divergence or infinite number. Okay, so if I do this one, then I'll put minus infinity to infinity e to the power minus at ut dt. Okay, and you know ut is nothing but it is the unit step function, and it varies from 0 to infinity. Okay, so then this the limit in the integration goes from 0 to infinity. Then write e to the power it is then e to the power minus at dt. Okay, and this one will be if this here, if it is a is less than 0. Okay, if a is less than 0, then if I put less than 0 means so negative of a, so negative of negative then becomes positive, so it will become e to the power at. So summation integration e to the power at from 0 to infinity, it go to infinity. Okay, so for a less than 0. Okay, so for a less than 0, I cannot go on finding out this x of t because it is not going to be a bounded one. Okay, so now if I go on it a greater than 0, so then e to the power minus at dt, so that means it will be decaying function. So this will be nothing but the curve will be like this. So this is a decaying function, go on like this. So yeah, this is t, this is x of t. Okay, so this one is nothing but e to the power at, e to the power minus at. So now if a is greater than 0, so then we can say this x of t is bounded 1, and we can go for the finding out the Fourier transform of this bounded signal. So now let us look at the Fourier transform of this signal x of j omega will be nothing but minus infinity to infinity e to the power minus at ut and e to the power minus j omega t dt. Okay, so then this one I can write then u of t is valid from 0 to infinity, so I can now put it here 0 to infinity, then e to the power minus of a plus j omega t dt. I can take like this. Now this is nothing but is the power series. Okay, power series of e to the power. Okay, so now let us find out its integration. So this will be nothing but minus 1 upon a plus j omega, and then e to the power minus a plus j omega t. So yeah, so this will be nothing but, so t will be here. Okay, e to the power j omega t, and this is 0 to infinity. So if I put this one, so e to the power if you put infinity over here in t, so this will be e to the power minus infinity. So 1 upon e to the power infinity, 1 upon infinity is nothing but 0. So this will be 0 minus of, then I put 0 in terms of t, so this will be to the power minus 0, so that becomes 1. Okay, so 0 minus 1, so it is minus 1, so this value will be minus 1, and this one becomes 1 upon a plus j omega, right? Okay, so this is the Fourier transform of the signal x of t, right? And now if you see this Fourier, this x of j omega, I can write this as a magnitude function. So x of j omega can be written as some magnitude of j omega, then its angle of x of j omega, right? So this is the magnitude response or the spectrum of the signal, and this is the phase spectrum of the signal. Okay, now let us look at the magnitude spectrum, how it looks like the magnitude spectrum. So this one will be nothing but mod of x of j omega. So if you take the mod of x of j omega, this is 1 upon mod of a plus j omega. Okay, and if you plot this one, so this will be nothing but x of j omega mod of x of j omega. So here this will be the omega axis. Okay, and when you put omega equal to 0, so this is nothing but, you put here omega 0, so that means 1 upon a plus j0, so that means it becomes 1 by a, so it is 1 by a. So now if I go on increasing omega with higher value, so in the denominator side, so there will be, the term will increase, and the overall value of mod of x of j omega will go on decreasing. Okay, so that means I'll have a decrement of this function like this, and this decrement go on like this. Okay, and similarly in the negative side also, so it will go on like this. All right, so if I put omega equal to a, okay, if I put omega equal to a, so that means at some point a value, so its magnitude will be 1 upon a plus j a. Okay, so to take the magnitude of that one, so this will be nothing but 1 by a root 2. So this value will be nothing but, I can write in the both side also, this value will be nothing but 1 by a root 2. Okay, so now if you see, the spectrum goes from 1 upon a to and go on decreasing, and it is symmetric also. In the negative side, the way it is decreasing, the similar wave it is decreasing the positive side of the omega, and it go up to infinity, right? So this is the magnitude spectrum, or the spectrum of the signal x of t. Right? Similarly, if you look at the phase spectrum, the phase angle x of j omega, so x of j omega, so it is nothing but the tan inverse of imaginary part divided by the real part of this x of j omega. So if you convert this one in a rectangular form of the complex number, so then you'll see the graph of phase spectrum of this function x of t will be nothing but x of j omega. Okay, and here it will go on antisymmetric fashion. So this will be nothing but go on like this, and at certain point it will go on decreasing. So yes, so this will be looks like this. So this one will be nothing but the saturation level will be at pi by 2, and this side also it is minus pi by 2. Okay, yeah. So and the value of pi by 2 will be start saturated at value of minus a, and this also will be getting at a value. So this is omega, right? So this is called your phase spectrum, and this one is called your magnitude spectrum. Okay, so that means whatever the information it is providing in the time domain x of t, it is same information we can get it by the signal representing the frequency domain, either in the magnitude spectrum or is phase spectrum. But in frequency domain, we can analyze the behavior of the signal and the system. Whenever this kind of signal will be applied to the system, the behavior of the system can be analyzed in a more better way rather than the time representation of the signal. Okay, so that's why you go on representing the signal in the Fourier domain. Okay, so Fourier transform is most important and most widely used Fourier representation of any kind of signal. Okay, because most of the natural signals, they are continuous and non-periodic in nature. Okay, so then when you go on discretizing this continuous time signal, then that becomes your discrete time non-periodic signal, and that will be nothing but the Fourier representation will be discrete time Fourier transform, that is DTFT, which is continuous and periodic in nature, right? Is it clear? Or any further question on that? If you don't have any query on that, so I understood that you all guys properly understand what is the Fourier representation. So this is all about the Fourier representation of different kind of signals, whether it is a periodic signal or in non-periodic signal, or it is continuous or discrete time signal. Okay, so according to the nature of the signal, so we discussed the Fourier representation could be of 4 types. Okay, so discrete time Fourier series, continuous time Fourier series, discrete time Fourier transform, and continuous time Fourier transform. So in continuous time Fourier transform, generally you consider this as a Fourier transform. Okay, and in continuous time Fourier series, we call it the Fourier series itself. Okay, so now let us solve another one problem in discrete time Fourier transform, as the Fourier transform is the most important one. So let us spend a little bit more time on looking at the Fourier transform of periodic and non-periodic signals and its continuous and discrete time signals. Okay. Now let us the signal is given as x of n in the form of like this. It is value is 1 when mod of n is less than n, and it's 0 when mod of n is greater than n. Can someone tell me what is this signal? What is the nature of this signal? What is the nature of this signal?
Step function.
Yes. Follow.
So step function.
Yeah, it is a step function. And what else? What other information? Yeah, it is a step function. But what is its nature? Which category it falls? Basically, that the 4 category of signal that we discussed, which category it falls? You see, it's very simple. You see, x of n is represented, and here this is the index is n. So if it is n, so it is obvious that it is a discrete time signal, right? And this discrete time signal only have value 1 when it is the index when it is less than equal to m. So after that it is 0. So that means the signal looks like this. So I can say this is 0, and then the value will be 1, and this is again 1, this is again 1, 1, 1, like that. It will go on up to here 1, and this will go up to m, and after m, so it is 0 values. The value is 0, 0, 0, 0. Okay. Similarly, in the negative side, so this is minus, this is plus 1, plus 1, plus 2, 3, 4, like this up to m. This is minus 1, minus 2. It will go on like this up to minus m, and its value is 1. Its all value is 1, and after that it is 0. Okay. All right. So this is my x of n. So it looks like a discrete time signal. So obviously it's a discrete time signal, and it has only value from minus n to plus m, and after that it is 0. So obviously this is a discrete time, a periodic signal. Okay. So there is no periodic repetition of the signal after the time index n. Okay. There is no repetition. So we say this is a discrete time aperiodic signal. Okay. So if it is a discrete time aperiodic signal, then what is the Fourier representation? The Fourier representation again would be discrete time Fourier transform, right? DTFT. So if it is aperiodic, then it is Fourier transform, right? And if it is discrete time, then it will be discrete time. So it will be DTFT. The Fourier representation is DTFT, right? So how do you represent the DTFT of this signal? So as you discussed, the DTFT can be written as x of e to the power j omega, or many book you can also find as j omega. Okay, this is the frequency. Omega is the frequency information, and this will be nothing but summation n equal to minus infinity to infinity x of n e to the power minus j omega. So this is the formula, right? Isn't it? So now you see this x of n is symmetric, is a symmetric function. So its value is same in the negative side from 0 to minus m, and the same value is repeated from 0 to m. So it is a symmetric function. So it shows a symmetric property. So I can write this one also instead of so this one has a equal to 0 to m. Okay, and that will be e to the power minus j omega n minus m. So I have used here the as given as equal to k. I've taken as m. So this one also I can write, or you can also simply go on putting m equal to n equal to minus m to plus m. That's the equivalent. Okay. So for simplicity of my calculation, so I have taken, since this is symmetry, so I can go on in this formulation. If I put m equal to n plus m. Okay. So whenever n equal to 0, so that means m is m. And whenever m equal to minus m, so m will be 0. And likewise, when n equal to plus m, so m will be m plus m to m. Okay, so that means I am covering from minus m to m. So this range entirely also covering in the summation, right? So now, if I factorize this one, this will be nothing but I can write e to the power j omega m. Okay, and then m equal to 0 to 2m e to the power minus j omega m. Okay, so yeah, so it will be put here yes, j omega m. So yeah, so this will be a minus m here now. So now if this is the function, so now this one is nothing but e to the power minus j omega m. So I can write this was summation of sine and cosine function. E to the power j omega is cos j omega plus minus j sine omega, right? And then if you solve this equation by factorizing this exponential term into sine and cosine, so yeah, so that will come as a function like this. This will be sine omega 2m plus 1 divided by 2. Yeah, so then sine omega by 2. Okay. Yeah, so it will come up like this. So can anyone guess what is this function? Can anyone tell me what is this function? Sine omega m divided by sine omega by 2. Okay, so this is sine. It's a function like sine pi x by pi x, right? So this is called a sinc function. Okay, this is called a sinc function. This is very, very important. Okay, so this is called a sinc function. And if you look at the magnitude spectrum of this sinc function, or the spectrum of this sinc function, it can be, you can see this sinc function nature is like this. So it go on infinity like this. Then after certain time, so it will go on increasing again. Like that, it will go on continuing. Okay, so this is the frequency axis, the omega axis, and this side also it will go on like this. Then it start increasing, and you'll have a function like this. Okay, so if you solve a little bit more into the sinc nature of the sinc function, so this is x of j omega. Okay, the Fourier DTFT Fourier transform, and this will be 0, and this one will be y. Okay, and this one will be also minus pi, right? So now you see the function is getting repeated across 0 to 2 pi. Okay, so this will be 2 pi, this will be minus 2 pi. So if you see 0 to 2 pi, so this is the same thing is getting repeated, just like what we discussed in the DTFT. So DTFT is nothing but the Fourier transform of the continuous time aperiodic discrete time aperiodic signal will be continuous in nature. In the Fourier domain, it is continuous in nature and it is periodic of period 2 pi. So the same thing can be observed over here. So it is periodic in nature from 0 to 2 pi, or we can say from minus pi to pi also, whatever the thing that is convenient to you. Okay. So this is the spectrum of this kind of signal. So if you look at this signal is nothing but a square signal. Okay, this is a square function which is sampled at equal interval from, and with samples of 2m. Okay, isn't it? So it is a sample of 2m. So yeah, so this is nothing but we call it is a for DTFT, discrete time Fourier transform. Okay, so from this we can find out its magnitude response and also phase spectrum, magnitude spectrum and phase spectrum. Both are different by looking at the spectrum itself. Okay, is it clear? So now let us solve another example. So if I give the signal like this in the frequency domain, so if the Fourier transform of a signal is given like this, it is 1 whenever mod of omega is less than w, and it's 0 from omega mod of omega less than pi. Okay, so if the spectrum is given like this, then yeah, then it has been asked to find out what is its time domain representation. Okay, find its time domain signal. Is the time domain signal. Okay, so if you see this one, it's the in the Fourier domain. So this looks like a square function. Okay, and the square function is having minus w to w, and from 0 up to w, this is 0 up to pi, and here also minus pi, this should be 0. Okay, so this is the signal in the Fourier domain. It is given, so it is x of e to the power j omega. Okay, so this is my omega axis. Okay, frequency axis. So now you have been asked to find out its corresponding time domain signal. Now, if you see, this one is a continuous. The spectrum is continuous in nature, and it is only valid from minus pi to pi. So we assume that again it will be repeating, maybe repeating after this pi. Okay, again. So that means this the time domain signal will be nothing but it will be a discrete time. Okay, discrete time aperiodic signal. Okay, so this will be a x of n. Now let us see how we find this x of n. So this x of n can be written as the inverse DTFT. Okay, so in case of inverse this DTFT, so x of n can be represented as 1 upon 2 pi, then minus infinity to infinity x of j omega d omega. Okay, and now I can write this as 1 upon 2 pi minus w to w e to the power because x of j omega is 1. Okay, minus w to w, within that interval it is value is 1. So I can write 1 into e to the power sorry, so I forgot to multiply here, e to the power j omega n here. Okay, that was the formula for DTFT, inverse DTFT, right? So now this will be e to the power j omega n d omega, right? So if you do the integration of that, so I'll get 1 by 2 pi into jn and e to the power j omega n. That means goes from minus w to w, right? Okay, and this one will be nothing but 1 upon pi n e to the power j omega w minus e to the power minus j omega w divided by 2j. Okay, so if this is the function, so this looks like, okay, this one, can you say what will be the value of this? What is the value of this? E to the power j omega w minus e to the power minus j omega w by 2j. So it is nothing but, I can write this as 1 upon pi n sine of wn, isn't it? The sine function can be written in terms of exponential function like this, isn't it? Okay, sine x is nothing but e to the power jx minus of e to the power minus jx by 2j, right? So that was the sine function. Okay, so now this would be the value of x of n. So if you look at, if I put n equal to 0, so what is the value of x of n at n equal to 0? So this will be nothing but this will be nothing but sine of omega into 0. So sine 0 is 0. So and 0 by this pi 0. Okay, so 0 by 0, so that is undefined. So this x of n becomes undefined, okay, for n equal to 0. But for next all other values except n equal to 0, n not equal to 0, so this function will hold good. Okay, so then again we have to find out some value of xn for n equal to 0. Okay, so to find out what is the value of x of n at n equal to 0, so how do you get the value, this one? Then I can use this as a limit of this function when n tends to 0. Okay, so that can be defined by using the L'Hospital rule. Okay, so if I use L'Hospital rule, okay, so this is a popular rule for getting the value of any function which is not defined. Okay, so this L'Hospital rule, if I apply, so I can write this as n tends to 0, 1 upon pi n sine wn. Okay, so that means this one I need to take it then the derivative for this kind of thing, limit. So the L'Hospital rule say that I have to go for a derivative of this function. Okay, so this will go on sine wn with respect to dn divided by sine pi n divided by dn with respect to n, right? So if you solve this one, so this will be nothing but w into cos wn divided by pi. Okay, and limit goes to n tends to 0. So if n tends to 0, so cos of 0 is nothing but 1, so I'll get w by y. Okay, so that means the value of x of n at n equal to 0, that means it will be x of 0 is nothing but w by y. Okay, so now this is the function inverse DTFT. Okay, inverse DTFT of the function x of j omega given like this. So that means I can write x of n as now 1 upon pi n sine omega n, sorry, wn. So this is nothing but it's a sinc function, isn't it? Okay, so it's a sinc function. So you can see in time domain also the sinc function looks like this. This is n. Okay, and this is nothing but x of n. And here the value will be w by pi, and this will be again pi by w. Okay, so yeah, so this I have drawn the envelope, but since this is n, okay, so it is a discrete time. So only I need to show the function like this. Okay. So yeah, so this is the representation of the signal in the time domain. Okay. This is the value omega by 2 pi here. Like that only. Okay. So you can omit the envelope now. So this will be the discrete time sequence. Okay. So this is a periodic signal, and it is discrete time. So if you take the Fourier transform of this x of n, this sinc function, so in the Fourier domain you will get a rectangular function like this. Okay, so that the same thing we have discussed over here. So in the time domain, okay, so you see the time domain, you got the discrete time, a periodic signal. So in the Fourier domain, so you got a function, a sinc function. Okay, so when you have in the time domain, if it is a sinc function, then its Fourier domain will be nothing but a square wave or the square function. Okay. So this is all about the different Fourier representation of the signal. So if you have any doubt, you can ask me now. Is there any doubt what you discussed till now?
Sir?
Yes.
Sir, in the previous one you said sine pi m by pi m sine. In the previous one, there was sine by sine, no sir. For that also you said it was sinc. Here,
Yeah.
yes, sir.
Yes. If you see, this is you can formulate this one as a sinc function, and this is. If you go on a little bit solving this one, so this will make a shape of a sinc function. Okay, but sinc function is sine pi x by pi x. Okay, so if I represent multiply over here, if I do some kind of mathematical trick by multiplying here omega 2m by 2 something, then some other multiplication over here. Okay, so this is nothing but the division of two sinc function, isn't it?
Okay, sir.
So basically, if you make a division of two sinc function, that will overall looks like a sinc function.
So basically, they have the same graph.
Yeah, they have the same. But you have to look at what is the value over here. Okay, so this one is very important. What is the value of at the zeroth point, and what is the first zero crossing? This point.
Okay, sir.
This is very important. Okay, and the nature would be like this. So it will go on like in the decreasing function. So then again after pi it starts again repeating. Okay, what is the value from minus pi to pi? The same thing will go on repeating after onwards. Okay, and most thing that you remember that this the time domain signal is a it is a rectangular discrete time signal. Okay, isn't it? This is a rectangular discrete time component, discrete time function in the time domain, and its frequency domain we are getting a sinc function. Okay, and the same thing if you see here, the time domain is sinc function, but its frequency domain is a rectangular function. Would you observe it?
Yes, sir. They are like inverse.
Yes. So now I can write this one like this. It is the rectangular function. And this side it is sinc function. Okay, so like if you go on from rectangular to sinc, okay, in time domain, so if it is if it is in time domain x of n, and this is x of omega in the frequency domain. So if it is a rectangular function in time domain, so in frequency domain you get a sinc function. And if it is a frequency domain, if it is a sinc function, okay, then sorry, if it is in the time domain, if it is a sinc function, so in the frequency domain we'll get a rectangular function. Okay, so that means I can say yes. So that means like if you go on changing the shape of the signal itself, what we are getting a similar kind of correlation. Are you getting my point or not? So the rectangular function, if I start with rectangular function, I got into sinc function, and then if I need to go back, so in place of sinc function, if I put a rectangular function in the frequency domain, so I'll go into the its corresponding sinc function in the time domain. Okay, so this is called dual property of Fourier transform, duality. Okay, so that means we can say sinc function, sec and rectangular function are duality. They show duality property. Okay, so I can go from rectangular to sinc, then I go on from in the frequency domain. If I put the rectangular function, then I'll get the sinc function in the time domain. Okay, are you getting my point? What I am saying? So this is called the duality property. So I'll come back to duality property a little bit later on when you discussed the properties of the Fourier transform itself. Is there any other question? Any other doubt? So if not, then let us wind up the class over here. So in next class onward, we'll discuss a little bit more property of the Fourier transform, and then we'll discuss some other aspects of the Fourier transform, its properties, then how do you utilize this property for analyzing a system behavior or system output. Okay. Is it clear?
Yes, sir.
Okay, so then let us wind up the class over here, and we'll meet in the next class tomorrow at 3 p.m. Okay. All right. So this is the end of today's class. So you now sign up the meet one by one.
Thank you, sir.
All right.
Thank you, sir.
Okay. Have a nice day.